consider, all possible networks are just 3 variables and see what is the best log likelihood they're able to reach. Notice that the log likelihood doesn't care about how you got there. It doesn't care about how the network looks. It just cares about how likely did you make the data. And so if you can reach a better value without being paranoid, then you yelled at me just now. You basically said you're being paranoid. That's when you get to say to people, you're being paranoid. There's a simpler explanation, which is in terms of observed variables. And why aren't you considering that? But in science, people have to be paranoid. Not everything is observed. Paranoia is a good thing. Okay, but these are very, very good questions. And in fact, the answer for your question is, the idea is that if you were to consider the best network on just these 3 variables, we expect that its maximum log likelihood would be lower than this. Otherwise, you're being delusional. You're being unnecessarily paranoid. Okay? The very last thing, since I said I will talk about this, I'll talk about this. So you have the expectation step and the maximization step. In the expectation step, you need to do inference. In the maximization step, you need to do learning. Inference can be pretty hard. We talked about in a whole set of lecture, at least one full lecture where I talked about how inference can be quite hard. So exact inference is actually, sharply complete. I was just saying, I just compute the posterior, but exact inference is pretty hard. Okay, and similarly, learning can be quite hard. If it is Bayes network with tabular representations of the conditional distributions, learning is easy. For any other case, such as connected parameters or parametric distributions, learning would be hard too. So computing the function maximum can be harder than just taking ratios. Computing the inference can be quite hard too. Now, and I need to do both of them for every iteration. Right? And that's not as good. So I will say that in this green, I'm saying, well, really, you don't need to be all that correct about inference. If you do, MCMC for a few steps and get a reasonable estimate of the posterior, even if it's not correct, that'll be fine. And similarly, you don't need to be all that correct about learning. If you take a few steps of function optimization, so notice basically what I'm saying here is, even finding the maximum of the lower bound can involve actual descent, gradient ascent. It may not just be simple ratio taking. Okay, and what I would say in this green thing is that even though it involves maximization, you don't need to really find the maximum of the current lower bound. Just find a slightly better point of the current lower bound. Going back again here, fortunately. So I'm here, I don't need to go here. Just getting here is still better, still fine, because then I'll get to here. Do you see what I'm saying? This way, I can at least do more iterations. Each iteration is of lower cost. And that is actually a very beautiful property for EM. Expectation maximization. Each of the steps, both the expectation and the maximization step, can be approximated, and still the thing will converge. That's a pretty powerful statement. When did you hear something like this before? What does this remind you of?
Clustering.
What?
Clustering.
No, you didn't hear from me. By the way, clustering is EM, by the way. That's like reverse. K-means clustering is just a degenerate case of expectation maximization algorithm. We just didn't think about it that way because K-means clustering is essentially hard clustering where examples will only, you'll never give it 0.7, 0.3. You will just say either 1 or 0. That means you take the posterior but take the maximum value and say that gets all the probability mass. That's fine. But in this class, have you heard, I'm asking for abstract thinking. Have you heard a scenario where you had multiple steps that needed to be done, but you said, oh, that step can be simplified as much as you want and you will still converge. If any of you give the answer, I'll give you 10 points extra. What? No.
Approximately for MVP?
I need example. I'm giving you a 10 points, so I need real example.
Modified policy errors?
Yes, 10 points for you. I don't know where I'm going to give, but that's correct. That's true. Okay? In modified policy iteration, basically we said policy iteration actually tries to solve the entire set of equations. And I said you don't really need to. Just do a few of the value iteration steps. You will still get convergence. That's the kind of thing that's happening here. I understand this is not the exact same problem. It's not the exact same theory. But, bringing back your background knowledge onto the problem is how you learn things. You learn it at an approximate level and then you learn it really. Okay? And so you have to look at this and say, yeah, this reminds me of something. And then finally, when you understand why it works, it might be working for a completely different reason. Or maybe connected reason. But in this particular case, this sort of reminds me at any rate, and of course at least one more person who just has background for modified policy iteration. Okay? I'll stop here. Next class, we'll start with base learning and LDA. Happy Thanksgiving and eat more raspberry bars if you feel hungry.